Hello and welcome to this video, which provides an overview of the material covered in Week 2 of EGR 280. In this week, we will learn the necessary information about random variables to support subsequent topics. To do so, we will cover two important random variables. The first is the binomial random variable, the second is the normal random variable. On the screen, we have a concept map that shows how probability theory, which is usually the model that underlies most statistical operations, is generally implemented using a random variable or multiple random variables. This more detailed concept map introduces several important ideas that will affect how we work with binomial and normal random variables. You can see that a random variable can be either discrete or continuous. A binomial random variable is an example of a discrete random variable. It has a probability mass function that describes the probability that the random variable will take a specific integer value. This graph shows the probability mass function for a particular binomial random variable. Each bar represents the probability that the random variable is equal to a particular value. So in this case, this bar here represents the probability that x is equal to 3. Binomial random variables give the probability that a particular outcome happens a given number of times in a sequence of identical and independent experiments. For example, if the experiment is whether a very cheap multimeter does not work properly when it is first turned on, a binomial random variable could give us the probability of 3 multimeters out of 100 not working properly. In this week, you'll learn how to compute the probability mass function for binomial random variables. In other words, you'll be able to create this graph for any binomial random variable. In this week, you will also learn how to compute probabilities associated with normal random variables which are continuous. As shown on this part of the concept map, probabilities associated with continuous random variables are usually formulated in terms of probability density functions and cumulative distribution functions. In this video, we'll explain the relationship between these two and how we use them to compute probabilities of events in the context of a normal random variable. An essential element in many statistical operations is to find the probability that a normal random variable is less than some value, something like this, is greater than some value, something like this, or between two values. Conceptually, these probabilities are computed as the area under the probability density below, above, or between values. So this is an example of a normal probability density. It's oftentimes represented as f of x. So to find the probability, say that x is less than some value a, the process I would use for a given value of a would be to look at the area under the probability density function to the left of a. The probability that x is greater than b I get by finding the area under the probability density function to the right of b. So finding these probabilities is essentially a matter of finding the areas under the probability density function. To find an area, we could integrate this density to get these areas. Or equivalently, we can compute these areas using the normal cumulative distribution function, which is an integral of the normal probability density. Now, in practice, there is no closed form for the normal cumulative distribution function. So in other words, there's no easy formula I can use to find out what these areas are. In practice, we either look up its value in a table or we use computational tools such as a spreadsheet or a calculator to compute its value. So one of the things you'll learn how to do this week is to find these areas. Another thing you'll do this week is, given an area, say you want to find an area of 0.2, find the value such that the area to the left of this value is equal to 0.2. This is sometimes called the inverse problem. One reason we use the normal distribution so extensively in statistics is the central limit theorem. The central limit theorem states that the sum or average of a large number of random variables has an approximately normal distribution, no matter what the distribution of each of the individual random variables is. As we will see in week 3, hypothesis testing involves comparing sample statistics, which oftentimes are averages, to thresholds. The fact that these averages are approximately normal means that we will use the normal distribution to make decisions about them. So, this concludes this video. Hopefully you now have a better picture of what week 2 will involve. Thanks for watching.